Lesson 3, Manufacturing Processes, Part 1. Manufacturing Processes. The world has come a long way since humans first made use of Earth's resources to craft simple weapons, tools, clothing, and cookware. Each era of human existence has experienced enrichments in product quality and diversity of products available for use. The Industrial Revolution was filled with great innovators and inventors and companies that catapulted technology and products into the future. This also spawned millions of ideas and experiments that have helped us to make the world a more comfortable place to live in. To become finished products, manufacturing is required to convert raw materials into finished products using machinery, labor, and technology to satisfy an intended purpose and design. Manufacturing, in its simplest definition, is changing the shape of materials into products, but in doing so can be a very complex system that follows a sequence of steps to turn an idea into reality. Manufacturing must optimize the selection of materials' properties, quality, quantity, and process variables to deliver the intended product and still make a profit. Manufactured products are an integral part of everyday life, but most people do not realize the great amount of investment and labor that go into each and every product. Although the manufacturing industry includes food, drugs, textiles, chemicals, and more, NDT is mainly concerned with engineering materials. Engineering materials are those that have reasonably good hardness, strength, toughness, and durability. This includes most metals, solid plastics, and some composite materials. This lesson is primarily focused on the manufacturing processes of metals by the conversion of shape, form, or properties of natural materials to include casting, metal forming, joining and fastening, metal removal processes, and surface treatments and coatings. Introduction: Casting. Casting is the process of pouring liquid molten metal into a mold cavity to solidify into a pattern shape. It is one of the most basic ways to produce shapes. Most materials used in metal manufacturing are cast at some stage within their processing. Castings come in a variety of sizes and metals. The vast majority of castings, from a tonnage standpoint, are made from cast iron. Whether cast iron or other metal types, casting starts with a design and specification to determine the appropriate process to follow. The casting process is fairly simple using a 5-step process performed in a foundry. Step 1. Select or construct a pattern. Patterns are 3D objects of the same approximate size and shape of the finished part, but having slightly oversized dimensions to allow for shrinkage during the cooling process, as well as material removal losses during the machining process. The simplest patterns are a single solid piece design, but more complex items require a split pattern that has 2 halves. Patterns can be made on a variety of materials, meaning wood, plastic, metal, wax, and so on, but they must be rigid and durable enough to maintain dimensions and withstand the pressures applied during the mold process in Step 2. Step 2. Select or construct a mold. A mold is made, or selected if ingot cast, using a variety of materials depending on the casting size, molten metal to be poured, pattern complexity, and quality of parts to be cast. The primary importance of the mold material is that it is made to 1. Hold uniform, tight compaction against the pattern surface. 2. Allow unimpeded, swift molten metal flow to fill the entire cavity. And 3. Maintain strength to hold pattern cavity position and tolerances during the pouring and cooling processes. The mold is designed in such a way that it can be opened for removal of the pattern. The mold container is called a flask, which contains an upper half, called the cope, and a lower half, called the drag. If the pattern does not have a means to channel the molten metal, then gates must be carved into the mold material to control the flow of metal into the cavity. At a minimum, sprues must also be carved into the mold material to form an entry point for molten metal to reach the cavity. Mold materials are generally made of green or moist sand or sand bonded with resin or clay. However, metal, ceramic, and plaster may also be used depending on the industry. Step 3. Melt material to be cast. Metal is added to a furnace for melting. Foundries follow known recipes to achieve prescribed chemical characteristics to adhere to a specific set of parameters and product specifications. These recipes use virgin or pure metal scrap metal, and alloy additive metals to make up the molten material. The melting process requires monitoring to ensure contaminants and hydrogen gases are removed. If the melt is of poor quality, the casting will also be of poor quality and will require scrapping or may create a discontinuity further down the process. In the melting process, the molten metal is always heated well above the melting temperature, called superheating. This superheat is necessary to hold the molten metal stage longer and improve fluidity of the liquid for pouring to prevent premature cooling during the pour into the room temperature mold. Step 4. Fill mold cavity with molten metal. Once the molten material is the proper temperature and the recipe is accurate per the chemical analysis, the molten metal is poured into the mold to fill the cavity completely. The entry point to pour molten metal into the mold is called a sprue and travels to the mold cavity through the gate. The pouring rate is critical. If the metal enters the cavity too slowly, it may cool before the mold is filled and may create cold shuts or misruns. If the pouring rate is too high, aside from being more hazardous, it will cause the walls of the mold to erode, resulting in sand inclusions and loss of detail in the casting. A high pour rate may also create casting surface anomalies due to premature cooling of splashed molten metal on the mold wall prior to being filled. Gravity is the primary mechanism for the molten metal to flow into all cavity orifices, but some complex cavities or narrow passages may require vacuum or pressurized gas to assist. Step 5. Casting product removal, cleaning, and inspection. After time has been allowed for solidification and cooling to occur, the upper half or cope of the mold flask is removed to reveal the metal cast object or part. A quick visual examination is performed to identify any immediate rejectable discontinuities. If there are no visual rejectable gross discontinuities, the solidified metal from the gate, runners, and sprue attached to the cast part must be removed by cutting them off, and the remaining mold material cleaned off. The casting produced is a finished product of the foundry. The cast part occasionally may be used in this form, but more often than not needs further inspection, meaning dimensional and/or NDT, and processing to improve surface quality or dimensions. Therefore, it becomes raw material for another processing area. Metal forming. Metal forming is the reshaping of metal through hot working or cold working without adding or removing any material, using one or more of the following operations: forging, rolling, extrusion, and drawing, as well as sheet metal shearing and bending. Hot and cold working. The difference between hot and cold working depends on the metal's temperature where grain recrystallization occurs. If processing the metal above the recrystallization temperature, it is hot working. If below the recrystallization temperature, it is cold working, typically at room temperature. Cold working. Cold working is the processing of the material below the recrystallization temperature. The metal is harder and stronger, but less ductile. Cold working produces a more finished and accurate dimensional end state. Forging. Forging is the process of working, usually hot working, ingot metal stock into a useful shape, size, and/or impression by hammering, pressing, or rolling. The purpose of forging is to confine the metal under sufficient pressure to cause plastic flow and form the metal into a desired shape and size. Forging will change the grain structure of the metal from a coarse grain to a finer grain structure, which will in turn increase hardness. If multiple passes of forging are required, the metal may require additional heat to improve some plasticity that forging has changed. Forging not only improves the strength of the metal, but it gets the final product closer to the physical dimensions to reduce material waste and time. Many discontinuities that were introduced in the ingot casting are weld mended due to the pressure and heat of the forging or minimized due to elongation of inclusions. Open and closed die forging. Open die forging, shown on the lower left image, and closed die forging on the lower right image, are the two primary means to forge metals. Open die forging provides a rough shape between two relatively flat dies to get an approximate shape and size prior to closed die forging. Rolling. One of the most common mill operations is the rolling of metal into flat, 2D formed shapes. Rolling is accomplished by passing the material between flat or shaped rollers to set up forces that squeeze the material and cause it to flow into an elongated form, while simultaneously the cross-sectional dimensions are reduced. For materials with low ductility and for large changes of section in any material, the work is usually done hot. For products that require a better surface finish and hold a tighter dimensional tolerance, cold working is required. Most products require both hot and cold working, as well as non-destructive testing. Flat rolling. Most materials start as cast ingots that are rolled initially into blooms, billets, or slabs. Blooms and billets are approximately square cross-sections of both large and small sizes. Slabs are rectangular in shape. All are destined for further deformation work by rolling, forging, or extrusion. Flat rolled products. Blooms, billets, and slabs are further reduced by rolling into flat rolled products of strip, sheet, plate, or bar, depending on the relative widths and thicknesses. Most are hot worked and cold finished by rolling. Form rolled products. A variety of other products, meaning rod, wire, pipe, tube, or structural shapes, can be made by using sequentially different processes that include rolling both hot and cold worked. Extrusions and drawing. Extrusions. Extrusion is the metal forming process that uses a ram to force larger diameter material through a smaller diameter die opening. As the material is pushed and squeezed through the smaller die, the material takes on the shape and size of the die opening and emerges as a smaller diameter extruded material. Drawing. Drawing is basically the same as extrusion, but instead of the material being pushed through a die, the material gets pulled through. Extrusion and drawing can be done by hot or cold worked metal, primarily with softer metals such as aluminum and copper. Sheet metal forming processes. Shearing. Shearing is the cold working process to cut or shear or punch holes in sheet metal. Bending. Bending is the cold working process to shape and deform sheet metal by bending or creasing the metal to meet a specific configuration, specification, or drawing. Joining and fastening. Other than new additive manufacturing techniques that use 3D printing, engineering structures rarely start out as a single part. Joining the individual parts and components together may be required to build greater structures and assemblies. The purpose of the joint is to keep assemblies or structures together while maintaining a designed and desired configuration, meaning part arrangement, orientation, and alignment, to allow the overall assembly or structure to perform its intended function or functions while resisting expected applied loads. The common joining processes are mechanical and metal fastening, adhesive bonding, shrink and press fitting, welding, brazing, and soldering. Mechanical and metal fastening. There are many different configurations of mechanical and metal fasteners available on the market to hold metal together. Bolts, washers, nuts, screws, pins, rivets, and anchors are just a few of the possibilities. Each has numerous different sizes, metal types, surface finishes, drive types, thread designs, hardness, and so on. Some industrial applications may make use of many different fastening options. However, a specification may require a specific fastener configuration to ensure optimal securement to minimize safety risks. Adhesive bonding. Adhesive bonding is used to secure two surfaces together to form a smooth bond. The use of glues, epoxies, and plastic bonding agents are typically used only in special structural joining applications and/or of a temporary bond until other stronger joining methods or techniques are completed. Although most glues and adhesives have relatively poor bond strength, many new agents are extremely strong and are slowly finding their way into the variety of applications where the environment, meaning the UV radiation, heat, and moisture, do not impact or degrade their molecular strength. In terms of NDT, the greatest advantage to adhesive bonding is that it distributes the stress load evenly over the joined or bonded area to reduce stress and fatigue discontinuities. Shrink fitting. Shrink fitting is another means of fastening metals by applying heat to a part so that the hole can expand to allow a room temperature or cooled piece to be pressed into the hole. When the two parts normalize in temperature, they become securely fastened by means of friction in a tight tolerance hole. Shrink fitting. Shrink fitting is another means of fastening metals by applying heat to a part so that a hole can expand to allow a room temperature or cooled piece to be pressed into the hole. When the two parts normalize in temperature, they become securely fastened by means of friction in a tight tolerance hole. If done correctly, shrink fitting provides a better bond than press fitting. Press fitting. Press fitting is very similar but uses high pressure versus heat to provide the same friction fit. And that concludes part 1 of this lesson.